Let's recall an example that we saw when we were looking at confidence intervals. We saw that Harris Health System, they said that they had 87% of their employees get a flu shot every year. That's what they expected, so they're going to take that to be true. We took a sample of 300 employees and found that 249 said that they received their shot. So with a confidence interval approach, what we looked at was we determined whether or not 87% seemed reasonable or not. And we did that by creating a point estimate and creating a confidence interval and looked at whether or not that 87% or that 0.87 proportion was contained in that confidence interval. That's different than what we're about to do, which is to use an hypothesis test, which is a formalized hypothesis test, to test this claim. So when we are creating and doing hypothesis tests, we want to assume that a particular claim is true. In other words, this is HHS. They say that the proportion of their employees that gets their flu shots is 0.87. So let's assume this to be true. Let's assume that the population proportion is equal to 0.87. That's going to be a first step, that we're just going to assume that that population proportion, and in future problems we'll have other parameters, but assume that it's true. What would that mean? Well, that means if this is the population, all right, this is the population, so I'm going to abbreviate this population, and we're going to assume that the population proportion is equal to 0.87. So that means when we create our sampling distribution, if we were to create a sampling distribution, remember that the sampling distribution, the mean of the sampling distribution, is also equivalent to the mean or the population proportion. So in this example, of our sampling distribution, we know that the mean of all the sample proportions would be equal to 0.87. So we know that if we took a sample and we wanted to compare where is that sample relative to the population, well, that population proportion is going to be in the center of our sampling distribution. If you need to go back and look at the sampling distribution module, then please do that. But we know that if this is true, let's just assume it to be true, then that means the center of our sampling distribution will also be 0.87. That's just what we know about sampling distributions. So what are we going to use that for? Well, in our sample, we had 300 employees, and we found that 249 of them, out of the 300, actually received their flu shot, just out of our sample. So if we calculate the p-hat, the point estimate, in other words, the sample proportion, 249 divided by 300, this gives us 0.83. Why is that going to help us? Well, let's assume again that the population is true. Our sampling distribution is made up of all of the possible and all of the proportions for each sample. So we found the one associated with 0.83. So if 0.87 is in the middle, then 0.83 is going to be a little bit here to the left. What we can do then is to calculate the probability that if the proportion for the entire population was contained or was actually 0.87 and we got a sample of 0.83, what's the probability that we actually get 0.83? If it's very low, then we could probably conclude that the population proportion in this case is not 0.87. So we assume the population proportion to be equal to their claim, we take a sample, and then we find the probability of actually getting that sample. And if that probability is low, then we would most likely say, you know what, that claim that they were saying is equal to 0.87, there's a very low % chance that that's true, or low probability that that's true. So hypothesis tests test a claim about a population parameter. And in this case, we were looking at the proportion. So there are two approaches that we're going to actually go about and use. One is called the p-value approach, where we actually calculate the probability. So in this case, if the population, if we assume that it's 0.87 and all samples, the mean of all the proportions here, was 0.87, what's the probability that we get 0.83? If it's less, let's say it's a 0.01 or 1% chance, then if that's the case, we would most likely say, you know what, this is unlikely to happen. This is unlikely to be the true population mean, or excuse me, in this case, population proportion. So actually physically calculating the p-value, and the other is called the critical value. The critical value. In other words, if we wanted to test this with, let's say, a significance of 0.05, we would find a critical value that would separate what's significant and what's not, and then we would look to see where is 0.83. Is 0.83 closer to the sampling mean here than the critical value or not? So again, we're going to get into examples, but the best thing for us to consider here is that if we were to assume that something were true, a value is actually equal to a population, or a population parameter is actually equal to some value, we take a sample and then say, well, if that is true, what is the likelihood that we got the sample that we did?